All right, it's that time. Everyone, that means you, someone, yeah. So today we're going to be talking about multi-layer perceptrons. We're kind of doing a little bit of a time skip because perceptrons were like, 50s, and now multi-layer perceptrons are like 80s and 90s. So we've time skipped a bit. We're not quite at modern yet. We'll get there. But multi-layer perceptrons, or MLPs, are very useful and are going to be the basis of basically all the machine learning we're going to do later on. So get comfortable with them. It looks like we have, it looks like homework one did cull the herd a little bit, but I hope that overall it wasn't that bad for you guys. All right, so let's remind ourselves of the perceptron, everyone's best friend. We have some amount of inputs that we take in this case 3. They go and through this weight layer, right, where we have one weight corresponding with each of the inputs. We take them all, and then we add a bias, right? Can't forget bias, can't forget bias. Later on we can actually. We'll get to that, and we do a summation where we multiply all of them, and then we add our bias. And then we also saw that we can add a threshold to it if we want to do classification. Right? We're going to generalize this concept of having this threshold today. And that will allow us to do multi-layer perceptrons. It's very good stuff. So let's remind ourselves of this interesting property we have with perceptrons. So we talked about this before. It is a refresher. Interestingly, education research says that refreshing and going over the same material is actually really good for learning it. And weirdly, so does machine learning research. There's a nice little parallel there. Anyway, so we wanted to do an AND gate. We wanted our thing to learn an AND gate, our perceptron. And we saw that when we do this, right, we can see that we just have 2 inputs, and we can set our weights. And we can think of our truth table essentially as our data. Right? If we want to do gradient descent, we can, or we can just manually do it when they're this easy. And we can see that for our model here, we can just set the parameters like so. And it works. Great. It will only output 1 when this truth table outputs 1 for those inputs. Great. But then we saw that when we start to try to do different gates, in particular an XOR gate, we have a little bit of issue. So we do the same thing. We grab the truth table. And then when we go to set the parameters for the same exact model, we realize we can't. And that's a pretty big issue for us because this is a very simple gate. If our core building block of all this machine learning that the whole world uses now can't do a very simple operation, a simple gate operation, then this whole thing is messed up. We shouldn't be using it, right? So let's think about why this doesn't work. And to do this, we can just graph the XOR, and we see that we end up with this, right? Where 1, 0 and 0, 1 are both green, and then 1, 1 and 0, 0 are both red. That's XOR. And we realize that when we try to classify this, no matter which line we draw on here, we can't separate the classes. This is an issue. And this, as we heard last time, is why perceptrons sort of died out in popularity for a long time. So, like I said before, it was roughly, this is why there's a bit of a time skip actually, is that once people realized that this could not do XOR, everyone said, all right, perceptrons are dead, who cares, move on, let's do the next thing. This happens a lot in academia, a lot more than you might think. And so, eventually, someone came up with a way to deal with this, though. And we have a nice little proof of an interesting property, which is we can have our perceptron here, and we're imagining that we just have some 2-input operation, right? And we want to do just now, instead of an entire truth table, a single example from the truth table. And we find out that there is a generalized way for us to set the parameters to do this. Right? I think take a second and talk to your neighbors and see if you can figure out the generalized way that we can do this. All right, just take a couple of minutes. All right, all right. Hate to cut you off. I know I always do it. Does anyone have any ideas of how we could set this? Yeah.
It's not possible.
Hmm?
It's not possible.
It's not possible? It is possible, actually. Good attempt at a trick question. No, it is actually possible. Anyone? So again, if we have a single example like this, yeah?
-1 and 1.
So -1 and 1 in this particular case, right? That is correct. And in general, what would we do?
In general, whenever we need the output of 1, we set weights to 1 and other weights to -1.
Exactly. So if we were to set all of the corresponding weights of 0 inputs to -1, and all the corresponding weights for every input that's a 1 to 1, then we realize that if we were to change any of the weights, we would end up with a lower number, necessarily. If we change any of the zeros to a 1, we will now be multiplying and adding a -1, which will reduce it by 1. If we change any of the 1s to 0, we're removing one of the ones we're adding, which is also a -1. So we have now very hand-wavy proven that we can, by that rule, separate out any single data. We can say, we will only say yes on this particular input, and everything else we can say no. We just set our threshold at right below its value and say everything else we don't care about because this is the maximum and it alone is the maximum. So that's just an interesting thing that we know we can do. We can literally separate any single point from every other point in binary space like this. Cool. So we can do this with any single input, like I just said. And OK, cool, maybe neat if you're into theory, but not particularly useful. So let's try abusing this new notion that we have. So we're going to take this, and we're going to build the same perceptron that we had before. Cool. But now we're going to also create a perceptron to do a different input. So this neuron right here, this perceptron, is only going to accept 0, 1. It will only output 1 on 0, 1. And this new neuron, we want to only output 1 on 1, 0. Right? So we draw it like this. Cool. And just for a little bit of notation, we're going to label the weights like so. This is just, if you ever see it, this is maybe helpful for seeing how we index weight matrices for later on. We'll say that if we're going from the first neuron in this layer to the first neuron on the next layer, so you see how they're both 1, then we say it's weight 1, 1, or 0, 0, if we're indexing by 0, which we should be. And then if we were to go from neuron 2 to neuron 1, then we say it's 2, 1, and then similarly with the other two. It's what it's from to what it's to. Anyway, so cool. We have one that will check this particular input, and we'll have one that checks another particular input. Why is that useful? Anyone have any idea of why that's useful? Give it a think. How about this as a hint? What are these inputs? So we're saying yes on these two particular inputs. Do they remind you of anything? They might remind you of XOR. Right, so how can we use this to solve XOR? How about that? Yeah.
or y1 and y2.
All right, and how would we do that just by using a perceptron?
Could we create a perceptron from y1, y2 to another, I guess, node?
Yes, we could. And in fact, we do that, and this will now be the output. And what should the weights be? Also you.
I mean, it could be w1
Not so they will have a particular value in this case. Anyone? Any thoughts? Sure.
1, 1.
Just 1, 1. So think about it this way. If we are accepting this input and we have it multiplied by 1, then we're saying this neuron will get a 1 when this particular input's seen. And if this particular input's seen, it will get a 1 from this one. So because there will only be one of them, we can say that this last neuron doesn't even need a threshold. We say that if it outputs 1, it means one of these inputs was seen. And if it outputs 0, then none of these inputs were seen. Interesting. This means now that this neural network, these three perceptrons together, are exactly doing XOR. So we've sort of stumbled across this idea that by adding multiple layers, we increase the computational power of a perceptron. And this gives us a multi-layer perceptron. And interestingly, we can use this exact same formulation to solve any binary circuit at all. Every single one. Imagine given some truth table, we pick out all of the ones that output 1. We create one neuron for each of them, and then we all OR them together. It's not an efficient way to do it. You can imagine that we'd end up with 2 to the n different neurons in the middle layer here. Not particularly useful. So that's not something that we'll actually end up constructing, although there is ways that we can get a little bit better than that. But for now, it's not particularly useful to approach this. Any questions? You all remember the awkward silence thing? I'm going to do that now.
Could you just go over again how, like, these values output 1, like, in these cases?
Yeah. So like we had before, so in the last slides where we really do that.
Yeah.
So we're setting it up so that when there is a 0 on the input, so we want it to only output 1 on this particular input. So what we're going to do is we're going to set, for every 0 in the input, we're going to have the corresponding weight be -1. And for every corresponding 1, we're going to have a 1, right? So when we add this up, we will get some value that is the number of 1s in the input. Yeah, it doesn't really matter. But why that matters is that if we were to change any of the weights from a 1 to a -1, we would necessarily be decreasing the output. So that means that this weight setting is the maximum, right? And for this input, I mean, so this input is the maximum. If we switch any of the inputs, sorry, I misspoke there, then we'll necessarily be decreasing it. So if we just threshold it right below that, then if we were to change any of the inputs, it would be lower. I'm not going to be particularly rigorous about proving that, but like it's pretty intuitive, I think, if that formulation makes sense to you. Cool. So we can do that, and then again, we just OR them together by having a new neuron with 1s as weights. So if that outputs 1, you get 1 from it. Yeah, that makes sense?
Yep.
Cool. All right. And thank you for speaking up. If something doesn't make sense and you don't speak up, I'm mad at you. All right. So this is our first formulation of an MLP, or multi-layer perceptron. This is what we're going to be doing for homework 2. Exciting. We're not going to be doing it like this, though. We're not going to be hand creating it. We're going to use our gradient descent. So let's think about what function we're actually doing here. All right, so now let's sort of generalize this and say, remember that we could have as many inputs and as many outputs as we want. And now we have this idea that we have this sort of middle layer, right? And it can have as many as we want. Right? It's a very general model. And if we're taking in some input, right? And remember that before, when we had the single layer perceptron, or just a perceptron, we were just doing a matrix multiplication, which is the weight matrix dot producted with the input. So now what operation are we doing? Give it a think. Yeah.
I mean, it looks like matrix multiplication.
So it is matrix multiplication, but we're doing a matrix multiplication. So let's say, like, if we looked at just from the first layer to the second layer, it's clear that that is similar, at least, to just a perceptron, which we can say that's doing a matrix multiplication. But then we have a second layer, right? So what we in fact have is a single matrix multiplication and then another matrix multiplication. Ooh, spooky. So this would be labeling these, so they're color-coded, so you can kind of tell how this works. You go from the in, out, right? Cool. Yeah?
We just take the dot product of the first 2 and then the dot product of the second 2?
Yes, exactly. So we're taking the dot product of the first layer, gives us the middle layer, and then the next dot product gives us the outer layer, right? So the end layer. Output layer is what we're going to call it a lot. So input layer, output layer, and then in the middle, we're going to end up calling this the hidden layer. Hidden because we don't know what its values are. We know what the input and the output are, we're given them, but the hidden values we're not sure on. And they're learned and there's something. So we're going to call them hidden. So this brings us to an interesting concept and a little bit of something that if any of you were really strong in linear algebra, you were probably yelling in your head, which is when we have this, which is just two matrix multiplications together, composed together, this is identical to some single matrix multiplication. This is just a property of affine functions. So I put here that it's any affine function. This is just true. Affine being essentially a matrix multiplication, any linear operation. There's a small distinction between linear and affine, which is the bias term. It doesn't matter. In our case, this means that having two layers is exactly the same as having one layer. So how were we doing something with two layers a minute ago that we couldn't do with one layer? Anyone? Any thoughts? Give this a think. All right. So everyone think on that for a second. It's also not a trick question. Now you guys can talk to your neighbors. Talk to your neighbors for a little bit about it. All right. So I want to hear what some people think. It's a sort of tricky question for all of you. Anyone have any ideas that they want to share? All right, let's start here.
I might be totally misinterpreting the structure of each one of the letters, but could the difference be that with B and A you can have two different matrices of like different sizes versus?
So it's a good thought, but in fact this is general. As long as the shapes make sense for B and A, then we have D, and D is actually going to be of the shape the first dimension of B and last dimension of A, and B and A have to share a dimension in the middle. But it is general to that. Yeah, we're just going to end up with a bigger matrix D. Yeah. Yeah.
I think because you want to specify like different inputs for a different application, so like you have a different dimension for the input, but then for the output you also have like a dimension of matrix that doesn't match the input, so you need a middle layer of like multiplications to like switch the dimension around and then like have the.
Yeah. So he's saying that because we're going from some input dimension to some other dimension, and then we're going to the output dimension, that that is why this is different than this. Funnily enough, and still a perfect good idea, that is actually equivalent to what he was saying, which is that we are having differently sized matrices, which is fine. It's covered in this case, actually. If we had a 5 by 1 and 1 by 10 matrix, B and A, then we would have some equivalent 5 by 10 D matrix. It's totally fine to do that. This is general to, again, any affine function. So anytime we're just doing anytime we're doing just multiplication and addition, this is true for any functions. It just so happens we're doing matrix multiplication. So I'm gonna give a hint to everyone to think about for a second, which is it would be true that if we were just doing matrix multiplication, that this would be the property. But I'm going to drop the hint that before, we were not just doing matrix multiplication. We were doing one other thing. What was that thing? Adding the bias. Not quite. That is still an affine operation, but that is true. That's not just matrix multiplication. Yeah. Transposing matrix? Transposing is still actually linear. That's perfectly fine. Doing a dot product is the same as doing a matrix multiplication. Totally fine. I think I saw a hand over here.
We're doing like a classification.
We're doing a classification. In particular, we were doing
0 or 1 based on how the linear combination of the inputs turned out. I don't know.
In particular, we're doing a greater than or less than. In particular, we're doing a threshold. You're right there. You're right there. I got you. So we're doing a threshold. And what's important about doing the threshold is that that threshold is not an affine operation. In fact, it is something in the class of what we would call a non-linear function. So we've now sort of gotten this idea that we could have two matrix multiplications with some sort of other function to separate them. And to make this a little bit more clear and vivid, we can say that we can turn our network into a nonlinear function by including nonlinearities. In particular, we can take this case where this is true, and if we were to include a nonlinearity in between the layers of the matrices, like so, we know that in fact it is very unlikely, but it's not always the case, that this is equivalent to a single affine operation. It's very unlikely that this is the case. So we now have this sort of theorem, this sort of idea for us. And how could we use this? Before we were using a threshold, and that's perfectly fine, but threshold isn't a particularly useful function. So we know that this is true for any nonlinear function. So why don't we poke around and try to find a good nonlinear function to use? So think about, for a second, with the people next to you, what properties we would want in that nonlinearity. What would be good for us? Think about everything we need to do gradient descent. Right? What do we need to calculate? What operations do we need to do? What would we want in this? Give it a couple minutes to think about it. All right. I'm gonna cut you off there. I'm gonna cut you off there again. So this is an extraordinarily open-ended question, and we haven't even talked about how we're going to train a model like this, which is different than before. But I still would like to hear where people are headed with this. So anyone have any ideas they want to share? This is, by the way, just to ease the pressure on this, an unanswered question. There's no correct answer of what property we definitely want. There's a list of properties that is consensus for the machine learning community that we like, but it really is an open question. So, yes?
Maybe it should just, like for these classification, it should be within a threshold, like 0 and 1 or something like that. So the activation function should reduce those values to them.
So we might want it to be between 0 and 1 for the sake of classification in this. Perhaps, I'd say even if we care about classification, we might want it to be bimodal, where it only produces either a 0 or a 1, which is what threshold does, but maybe we want it in some other way. Cool. Yeah, back there. The function should be differentiable. Good thought. So we are, at some point, presumably, going to do some differentiation, however we do it. And it is going to be the case that we are going to, at some point, need to differentiate this nonlinearity. We can think about using a threshold, and we can realize that that is what we call a step function, and that is not differentiable. So, in fact, using the threshold causes an issue. So we do want it to be differentiable. Cool. Any other thoughts? There are more than just that. There's plenty. Yeah. Ooh, restricted output so that it doesn't explode and get really large. That is going to be an important property, and we can talk about that. It's and weirdly, the solution ends up being worse than the problem, but we'll get to that. We'll get to that. So those are some good ideas. Those are some good ideas. Anything about it. And if you couldn't really think of anything particular, that's because I haven't talked about nonlinearities at all yet. So it's totally fine. So let's talk about them then. So the one that I put on here, which is one of a few that we're going to talk about, is that we would like it to be differentiable, and in particular, we want it to be very quick to derive. We're going to be ending up, now that we're in the realm of multi-layer networks, things are about to get a lot slower for us. This is where we start to have issues. So we want our nonlinearity to be very easy to compute the derivative of, and the forward pass of. We want forward pass being just calculating the function. So we want both of those to be very quick, if we can. So let's talk about 3 major ones that are used and talk about the pros and cons of each. So first up is sigmoid, which is the function 1 over 1 plus e to the x, where x is the input. That looks a little something like this. Cool. That's what it looks like. So it's squeezed in between 0 and 1. Sort of like Rashir was saying. And it has this little slope where it hits hits exactly 0.5 on the y-intercept. Neat. All right. This is its derivative, though. All right, just let that, think about it. So that is, its derivative is 1 minus its output times its output. Okay, neat. Next up is tan h. Tan h is very similar to sigmoid, but with a little bit of a difference. Its difference is now it is 0-centered, and it squishes it in between -1 and 1. So it's a very similar function. And similarly to sigmoid, its derivative is also only going to use simple operations and its output. So it'll be 1 minus tan h squared. Neat. Okay. And lastly, and sort of an outlier in this group of 3, is ReLU. Yeah, I heard it over here. ReLU is very famous, so that's why someone might know it. And ReLU looks like this. Now you might be saying, Cooper, that's not a nonlinear function. You can't fool me. Turns out that piecewise linear functions are in fact nonlinear in the mathematical sense, and importantly, in a practical sense. It does work. So what's nice about ReLU is you can see that it's just a maximization between 0 and the input. And its derivative is either 0 or 1. Those are the only options. If it's greater than 0, then it is just 1. It's just a complete line. It is y equals x. Otherwise, it's 0 because it's flatlined. All right. So let's think about what the pros and cons of this might be. So in general, I'm going to spoil this fact. Sigmoid is not very good. So I want you to consider for a moment why sigmoid might not be good. All right. So I'm going to give you 2 or 3 minutes to think about this question and talk to your group. All right, go. All right, I think that's enough time thinking about this one. I would like to hear what people have to say, though. There's a whole lot of debate you could have about this, actually, so I'd like to hear what people think. Anyone? Yeah?
So for sigmoid, every single time that you take the derivative, you have to solve for sigmoid again. So then if you found the derivative of the derivative, you're going to have to solve sigmoid 4 times, and then on and on and on.
Interesting observation, and we will get to that. So to spoil a little bit of the story going forward, basically, once we solve it once, we will never solve it again. That's a beautiful algorithm that we're going to get later down the line, is how to do that in an efficient and algorithmic way of not needing to recompute things. And you're actually going to see on homework 2, you're going to have to do that algorithm, and you'll see that it is pretty amazing how much computation you save by doing that. It's a good observation. We needed to fix that problem. But it's not a coincidence that those two at the top there have their output in their derivative, because that is actually a nice thing for us. Cool. Here, how about, okay, he had a good observation. Would you like to share yours?
I think the first one cannot show the negative outputs, but the second one, it can just attach negative ones. So I think that's the reason why the second one is better than the first.
Yeah, so the observation is that sigmoid here never outputs anything negative. Neither does ReLU, but if we think about it, there might be some sort of loss of information there. There is a difference, a very stark difference between -1 and 1 that there might not be between 1 and 2. Having a negative sign does change an operation pretty significantly. So if it doesn't cross over into negative outputs, maybe we're losing information. Maybe there is some loss of expressibility here. And in fact, there is a little bit. We can deal with it in different ways. But that's why people want to do tanh. We'd like this sort of proportionality where we have negative numbers that are different significantly than positive numbers. So we liked tanh for that reason. Anything else? Yeah?
As x gets very small or very large, the derivative you need very precise variables to store that.
Oh. All right, yeah. So what he's saying is that if x gets very large or very small, the derivative gets very, very small, and we need very precise ways to calculate it. And there is actually another big issue with that. Having derivatives very close to 0, you can imagine in some way, I know we're not there yet, but you can imagine in some way that the derivative of this will be somehow related to our gradient. And if the derivative of this is really small, perhaps our gradient will be really small. And that means we're learning very slowly. And that does become an issue. So it is a very serious issue of this. So those are, I'll take those. There is also an observation that I think I heard around, which is it doesn't pass through the origin. So zeros might also have some significance in all of this. And if we are turning zeros into positive numbers sort of arbitrarily, that might be a problem. We're not really sure, like as a class, but maybe it is. So a whole bunch of reasons to be skeptical of this. Let's look at the second one. So the second one is a bit better empirically. It just does a little bit better. But does it have the same sorts of problems? And we can go through the ones that we want. It does pass through the origin. It does have negative numbers. But the derivatives still do go to 0 as we have high magnitude inputs. That's not great. So that brings us to ReLU. And to spoil the story a little bit, this is the one that everyone uses. Because, and this is tremendously disconcerting to me, it does the best. That is the reason that we use it. There is no consensus on why it works the best. What? There's ideas. It's easy to do computation. Maybe in general people compute more with it. But it just works the best. The person who invented it said, I tried out a bunch of stuff and this one worked the best. There's a reason for it. It has very good derivatives. Yeah?
Why is it called ReLU?
It's a rectified linear unit. So it's rectified because it's just a threshold. Rectification is thresholding, and then it's linear because the rest of it is linear. So rectified linear unit. It's weird, and the fact that it does, where we said before, oh, we might want to have the outputs be squished to some value so they don't just keep getting bigger and bigger or whatever. This one doesn't do that. It doesn't care, but it works the best. So if you can figure out the reason why ReLU works better than these other two, congratulations. You can write a paper and have a TED Talk for all I care. It is a big deal that we don't know why that works. It is used in almost every single machine learning model these days, and we don't know why it's the best. Anyway, open area of discussion, and coming up with new nonlinearities is an open research question, but it's a hard question. Again, the person who invented rectified linear units spent 20 years just trying to come up with a better nonlinearity. He came up with this, and he didn't have a reason. He didn't not have a reason. He had a rationale, but he didn't have any proofs. Anyway, so now it's time for something else. Anyone want to guess what it is? Anyone who read the syllabus? It's a quiz. Yeah. Just kidding. Not yet. Now, we're gonna introduce another new notation. We're getting to the quiz, don't worry. So we're going to introduce another new notation. I know. But this one's just helpful for like when you're reading papers and when you want to very quickly write a model. And it'll also allow us to introduce a new sort of thing. So before we had a single perceptron, right, which we drew this way. Before we just had regular notation, but now we have perceptron. It became a multi-layer perceptron. And our new notation, because this is a bit awful to draw and really awful to put in Google Slides, we have this. So each one of these is going to represent a fully connected layer. That's what that FC is. Fully connected, meaning that every single one of those nodes has a weight to every single other node in the next layer. So we say it's fully connected. You might also call these linear layers. We do that later on when we use something like PyTorch. And now we're making an amendment to this where we are adding these functions in between these layers. And this sigmoid or the sigma letter is going to be the general symbol that we use to mean nonlinearity. So we are going to have fully connected layer, nonlinearity, fully connected layer, nonlinearity, fully connected layer. This is generally how models are going to be drawn in like research papers. And if you want to quickly communicate what model you're using, you do something like this and then put the shapes of each of them on them. Anyway, so that is going to be a notation that is common. Yes?
So what is the reason, again, why we have to use nonlinearities in these functions?
Essentially, and this gives us a very nice, actually, theorem, which is that when we have if we don't have nonlinearities, then our entire model is essentially just a linear operation. It's equivalent to doing a matrix multiplication and adding a bias. That is what our model is doing. As many layers as we add, that is what it's doing. So as soon as we add any nonlinearity into it, we cannot combine them into a single linear operation anymore. And in fact, the model itself is now some nonlinear function. And in particular, we have a very nice theorem that says, if we have a model like this, then given any nonlinear task whatsoever, we can increase the size of these layers, like those hidden layers that we didn't know before. We can increase them such that we guarantee that the loss is within any threshold we set of the optimal. So we can guarantee by adding these nodes, we can approximate any function at all. Wacky. Arbitrarily well, too. And this is called the universal approximator theorem. It's very, very interesting. It's not practical because we can add infinitely many nodes, essentially. It will be some number of them, but we add as many as we need, which is not practical at all. Anyway, so it's an interesting theorem. That is why we add nonlinearities, because we want to be able to solve nonlinear functions. It's exactly so that we can solve something like XOR. Anyway, so now it's quiz time. Yeah. So one person from each group come up and grab the quiz and pass them out. Yep. They're in the stack. I believe in you all. All right, so once again, you'll have 15 minutes to do this. And I'll remind you right out the head of it, because apparently people didn't pick up on this. Every quiz, everyone will get 100 on. These are just for like fun, I guess. They'd help you learn and to be able to talk about the answers. Do try them though. They're fun questions, I think. All right, 15 minutes, go. By the way, to answer that question, infinite means countably infinite or higher. If you have a question, by the way, do raise your hand so I can clarify for everyone. on the written question, by the way, the function does have x with a 2 superscript. That is x squared, not x, like not the second dimension or second input. That's why we have the weird notation. I'll answer this question because I bet a few people are stuck on this actually. Just to remind everyone, the gradient of f with respect to w, which is what we're doing at the bottom, means the partial derivative of every one of w, every element in w. So the partial derivative of f with respect to every single one of w. Help you work on the last question if you were stuck. All right, that's time. So just to make sure we're all on the same page, this quiz is still hard. It's a little bit easier than last time, but if you got all the questions and you feel confident about them, you not only have gotten 100% of what I've talked about in class, but you also already knew stuff probably. These quizzes are supposed to introduce ideas to you, so it is perfectly reasonable to not be able to do stuff. But some of the stuff you should know how to do, so it should give you an idea of what you need to brush up on. Anyway, so let's do the answers now. I'm sure you're all dying to know. So, I missed one animation. All right, whatever. So, let's start with the first question. Imagine we randomly choose half of our data set, x's and y's, that's our data set, and train our model on it until we have very low loss. The model will be able to perform as well on the other half of the data set. So the way we're going to do this, and also I want to clarify something because some people apparently think this class ends at 6:30. It doesn't, it's 6:45. You're stuck with me for another 15 minutes. So talk to the person next to you. So pick like 1 or 2 people to talk to and talk through your answers with them for a minute or 2. Go. All right. I did say a minute or two. So ready? We're gonna do thumbs again. We're gonna do thumbs again. So thumbs up for true, thumbs down for false. Ready? Go. Oh yeah, lots of thumbs down. A couple thumbs up. All right, I like it. All right, and the answer is false. So I'll give you a little bit of a reasoning here. There's a couple things that give away this. For one, as well, it is not trained on that data, so you can imagine it will be different, and we'll see that in a second. More generally, this is the idea of, it could be the idea of overfitting. We're given some partial data, we fit extremely well to it, so precisely well, that no other data from that distribution actually really is represented by our model. And we'll see that right now. So we can imagine that we have this data, which is already fit by that line. And we can say, OK, this is the data that we're given, and let's fit really well to it. And that's a reasonable fit to that data, right? Now let's see the entire data set. So here's the entire data set now. And all of a sudden, that line does not look so good. In fact, all those blue points, I'd say that is a bad prediction for all of those points. A more reasonable guess would be something like that, right? So we can get an issue where when we fit very well to some data, we will be able to not fit to the rest of the data. Yeah?
So my only question is how, like, I guess randomly if you chose data, you could just get the top half of that, but this seems to have only gotten like top half of data randomly. So
This is an extreme example for this very simple case, but when it comes to like more complicated models, more complicated data, it is really an issue. Even if we randomly sample from the exact same distribution, distribution just being like how the data is spread out in space, then we can actually still, like we get this problem all over the place. So this is an important issue. And randomly choosing, even if we're doing it randomly, even if we're sampling it perfectly, can still cause some huge issues, as I've said. And it doesn't really leave any noise if we fit very well, is also another word here that I say. We fit to it very well into a very low loss. The problem there is it doesn't leave any leeway for bias in the data that we randomly chose, and also in noise that might exist in the data set. So we're just imagining here that, oh, this is the perfect data, but that's not true. All right. Question number 2. It is possible for there to be infinitely many different initial parameter values for our model, which all reach different optimal parameter settings via stochastic gradient descent. So again, talk for a minute or two with the people next to you. Talk first. All right, that's a minute or two. So, thumbs up for true, thumbs down for false. All right, more of a split on this one. I like it. This is a bit of a weirder question. And the answer is true. So I'm going to give you a really cheesy, half-assed example that is absolutely true and does prove this case. But I will tell you that it does generalize. So imagine a really weird case where our loss function, for whatever reason, is just sine of our weights. So So we have one-dimensional weights, and we have sine of our weights. And you might be saying, doesn't our loss function have to be with respect to our prediction and the true label? No, it doesn't. Who told you that? So we imagine our loss function is sine of w. Then we have the case that essentially we have a sine function, just exactly a sine function. And there are optimal parameters for this. There's infinitely many optimal settings of these weights, which are the multiples of 2 pi. The multiples of 2 pi plugged into sine are all 0, and there's nothing lower. So we imagine if we pick any point next to them, or if we pick any multiple of 2 pi, there are infinitely many of those places where we would descend into different optimal parameters. That feel okay for everyone as a proof? You might have a problem with the fact that I have a loss function that's not based on the prediction or the label, but it's perfectly fine, trust me. So there are also real loss functions that would have infinitely many. It's the exact same question. Is exactly equivalent to asking if there are loss functions that have infinitely many equally optimal points. And if you do, then that is like locally, that means that there is a little divot that you could do stochastic gradient descent into. This is just a really cheesy proof. All right. Yep, so I already said that. Okay, next question. A single perceptron with integer weights can perfectly, with 100% accuracy, separate any linearly separable data. All right, talk to your neighbors, 1-2 minutes. You know the drill. All right. Oh, man. All right. My lapel fell off, but it's okay. We will proceed. So we're doing thumbs up and down again. So up for true, down for false. Go. Ooh, a spicy split. All right. Yeah, that's like 50-50 split. And the answer is false. Yeah. This one's a bit of a fun one. It's a bit of a more theoretical result. So we can imagine that there's a case where if we change our weight by 1, it's essentially jumping over. If we have 2 points that are too close to each other, changing our weights by 1 will capture both of them, where if we had a smaller number, something smaller than an integer, maybe something with higher resolution, it might be able to squeeze in between them. Same goes for bias, by the way. There's not any difference there. So this begs an interesting secondary bonus quiz question, which is I'm saying this has like too low resolution. So how about something with a higher resolution? Rational numbers. Anything representable by a fraction. So give that a moment to set in and think about. All right. Now that you've had a second to get your gut feeling about it, we're doing thumbs up and down again. Can rational weights do it, or can they not? Well, guess what? They can't. Yeah. To be able to do this for any for any linear separation, we need unbounded precision real value numbers. Crazy. That's a ton of precision that we need for just linearly separable. The real secret here is that for integer data, we need integer weights. For rational data, we need rational weights. And for unbounded real value weights, which could still exist, input, we need those kinds of weights. You can go ahead and try to prove this to yourself at home, but you can just accept it as a theoretical result if you don't want to. There's some interesting corollaries here to like Turing machines and stuff, so if you're interested in that, there's some good literature on it. Anyway, so next, the actual written question. I'm going to skip going over like talking with your teammates. I'm sorry about it, but we're close on time. And I want to do the advice today. I missed it last time because I had a migraine, but today I'm not. So imagine we have data with one feature. So that's just a single data. So it's like these 2D things that we've had before. And with n different data points. We have this model where we're taking different powers up to n of x and multiplying them by weights and adding them. So what is the issue that might come from training this enough with the weights, with the values of the weights in particular? So I'm sort of fishing for a particular answer here, but there are a couple things that you might want to say. I'll just spoil the story for you and say, when we are doing this, when we have the n different powers of x and we're fitting weights to them, essentially what we're doing is we're creating an n-degree polynomial. And something you might remember from pre-calc and whatnot, if we have n points on something, and we want to fit an n-degree polynomial to it, we know that we can exactly. So this means when we go to train our model, we will find the polynomial solution to exactly fit those points. And the problem is, with real data, it's very likely, actually, that the weight values that are needed there, the things in front of the polynomial terms, will need to be extraordinarily high. They need to be like 10 to the 50th, ridiculous things. And we can't even go outside of the bounded precision that we have on our computer. So it's very likely that sometimes we will just have weights that increase infinitely. We don't want that. For one, it might break our computer. And two, it means that if we were to take another point and try to fit it, like if we had a line and we fit it like boom, 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 and we try to put another point on that line, we would get it so wrong. So it doesn't generalize at all, and it